Element 24, chromium. The hidden metal behind stainless steel, brilliant colors, and one of chemistry's most fascinating stories.
If I told you to look closely at your stainless steel kitchen sink, right, and then look at a sparkling green emerald in a jeweler's window, and then, I don't know, a heavily regulated toxic waste site, you probably think they have absolutely nothing in common.
Right. I mean, you'd think they were completely different worlds.
Exactly.
Yeah.
But if you zoom in close enough, down to the atomic level, you find that they're all dominated by the exact same atomic building block.
Which is just, it's a beautiful illustration of how elements actually behave. Because we have this tendency, to look at the periodic table as this menu of fixed static ingredients.
Like iron is strong, gold is shiny, lead is heavy, that kind of thing.
Yeah, exactly. But element 24, chromium, it completely shatters that assumption. I mean, it is a masterclass in how an element's identity entirely depends on its atomic form and its chemical context.
Welcome to the deep dive. Today we are tracing the story of atomic number 24 as part of the Atomic 118 project. We're looking at chromium, and the mission here for us is to solve a paradox.
A pretty massive one, too.
Right. How can one single element act as the invisible shield that protects modern infrastructure from decaying, paint the Earth's crust with the most brilliant colors imaginable, and simultaneously harbor this really dark, dangerous alter ego?
To understand that paradox, we actually have to start with the aesthetic side of the element, which I find fascinating. Long before chromium became this structural heavy lifter of the industrial age, it was making waves in late 18th century Paris as, well, basically a visual spectacle.
Oh, wow. So we're going back a bit.
Yeah, the year is 1797, and a French chemist named Louis-Nicolas Vauquelin is analyzing a highly unusual mineral. It's called croquite.
I can just picture this scene, in a dimly lit Parisian laboratory.
Yeah.
Because croquite isn't some dull gray rock you'd find in your driveway.
Oh, definitely not.
It is this striking, almost unnatural-looking, bright red-orange crystal. I think it was originally found in the Ural Mountains in Siberia.
Oh, that's right.
And it was so vivid that painters and chemists alike were just obsessed with it.
And Vauquelin was trying to figure out what was responsible for that intense color. Because croquite is a lead mineral, but the lead wasn't creating that red-orange hue.
Right. Lead is usually pretty dull.
Exactly. So through a series of acid treatments and precipitations, Vauquelin manages to isolate a brand new metal. And he realizes really quickly that this new element has a highly unusual property.
Which is?
Well, depending on what he mixes it with, it produces an extraordinary spectrum of colors. We're talking deep greens, brilliant reds, vivid yellows, and rich oranges.
So he names it after the Greek word chroma, meaning color.
A very fitting name, because for the next century, chromium's primary job in human society was artistic.
It was essentially high-end paint, right?
Basically, yeah. Chromium compounds became the foundation for some of the most durable and vibrant pigments in the world. Like, chromium oxide produces this dense, opaque green that painters absolutely relied on.
I am struggling a bit with the mechanics of this, though. Like, how does one single metal produce so many wildly different colors?
It's weird, right?
Yeah, because usually a pigment just absorbs certain wavelengths of light and reflects one specific color. Why is chromium acting like an entire primary paint palette?
It all comes down to its position on the periodic table. So chromium is a transition metal, which means it has a very specific configuration of electrons. Specifically, its d orbitals are only partially filled.
Okay, you might have to break down d orbitals for me.
Right, so think of them as these outer layers of electrons that are loosely bound. They are highly sensitive to their chemical neighborhood. So when light hits the chromium atom, those electrons absorb certain wavelengths of energy and jump to higher states.
Okay, I follow that.
But the exact amount of energy they absorb shifts dramatically depending on the atoms surrounding the chromium.
Oh, I see. So it's not the chromium itself that is intrinsically red or green. It's the relationship between the chromium atom and whatever it happens to be bonded to.
That is a great way to look at it. If you bond chromium with lead and oxygen, the electron gaps shift to reflect that bright croquite orange. But if you bond it differently, the gaps shift again, and the material reflects a deep, permanent green.
Which brings us to emeralds.
Yes, exactly.
Which is wild to me, because emeralds are one of the most prized gemstones in human history. And the fundamental structure of an emerald is a mineral called beryl, right? Which is naturally colorless.
It is. It's just clear crystal.
But if you have even a microscopic trace of chromium infiltrating that crystal lattice while it's forming deep in the Earth's crust.
The entire stone transforms. It's incredible. The chromium atoms basically substitute for aluminum atoms inside the beryl crystal.
Slipping right into the structure.
Exactly. And because chromium is just slightly a different size, it distorts the surrounding crystal lattice just a fraction of a nanometer.
A fraction of a nanometer, that's barely anything.
Right, but that tiny mechanical distortion forces the chromium's electrons to absorb the red and yellow wavelengths of light, allowing only that mesmerizing, glowing green to pass through to our eyes.
That is unbelievable. Just a few stray atoms of element 24 distorting the local architecture, and a clear rock becomes an emerald.
It really highlights how sensitive it is.
Yeah, but that manipulation of light and crystal structure leads to my next question. How does something that delicate an element, literally named after color and famous for, art transition into the gritty, heavy-duty world of industrial machinery?
Well, the transition hinges entirely on metallurgy, because for a long time, chromium was actually too brittle to be useful on its own as a structural material.
You couldn't just build a bridge out of pure chromium.
No, it would shatter. The revolution happened when metallurgists realized that if they could force chromium into the structural matrix of other metals, specifically steel, they could fundamentally alter the physical limits of that steel.
And when we talk about the limits of steel, we are really talking about its fatal flaw.
Rust, the enemy of engineering.
Right, iron is the backbone of steel, but iron has a deeply self-destructive relationship with oxygen.
Rust really is the great destroyer of human infrastructure. When ordinary steel is exposed to moisture and oxygen, the iron at the surface undergoes an electrochemical reaction, and it forms iron oxide.
But the real issue isn't just that it oxidizes. I mean, aluminum oxidizes, copper oxidizes. The specific problem with iron oxide is that it's physically larger than the iron it replaces, right? It swells.
Yes, exactly. The crystal lattice of iron oxide does not match the iron beneath it, and because it expands, it creates immense physical stress at the surface.
Like an expanding ice cube in a glass.
Great analogy. It gets brittle, it fractures, and eventually it flakes away. And that flaking exposes a completely fresh, vulnerable layer of raw steel to the environment, which then oxidizes, swells, and flakes again.
It is just a relentless, continuous cycle of decay.
Yeah.
And it'll eventually eat through a bridge support or a building frame until the whole thing collapses.
Enter chromium.
Ah, the savior.
Exactly. When metallurgists began mixing element 24 into steel, they discovered this magic threshold. If you add at least 10.5% chromium by mass to the steel alloy, the metal stops rusting.
We call it stainless steel.
Right. But here is what's counterintuitive about it.
Yeah, because here's what I don't get. If chromium is a metal, shouldn't it oxidize too?
Oh, it does oxidize. In fact, chromium is far more reactive with oxygen than iron is. It oxidizes significantly faster.
Wait, if it reacts with oxygen faster than iron, shouldn't it be even worse for the structure? How does rusting faster equal stainless steel?
Because of the type of oxide it forms, this is the absolute superpower of chromium.
Okay, I'm listening.
When that alloy is exposed to the air, the chromium atoms at the surface basically race to grab the oxygen before the iron can, and they form chromium oxide.
Okay.
But unlike iron oxide, chromium oxide is incredibly dense, and its atomic spacing perfectly matches the steel alloy underneath it. So it forms what is known as a passive oxide film.
Ah, an invisible shield.
An invisible, impermeable shield. It is only a few nanometers thick, literally a few atoms deep, but it fits over the surface of the metal like a perfectly tailored, airtight skin.
So it completely blocks any further oxygen or moisture from penetrating down into the iron.
Exactly.
So instead of trying to build a wall to keep the oxygen out, chromium acts like a diplomatic envoy that rushes out, forms a permanent alliance with the first wave of oxygen, and together they become this impenetrable border wall to protect the iron inside.
That is a perfect analogy, and the most remarkable part is the kinetics of it, because it is entirely self-healing.
Wait, self-healing how?
Well, if you take a sharp knife and deeply gouge a stainless steel countertop, you physically break that invisible shield. You expose raw iron and chromium to the air.
Right.
But within milliseconds, the newly exposed chromium atoms react with the surrounding oxygen and immediately stitch the barrier back together.
Wow. It weaponizes the very element oxygen that wants to destroy it and uses it to cure itself.
Which completely changed the economics and the safety of modern engineering. I mean, stainless steel isn't just one metal. It's a massive family of alloys tailored for different extremes. But that 10.5% chromium is always the gatekeeper.
And once you know it's there, you realize this passive oxide layer is quietly holding modern civilization together.
It really is, everywhere you look.
It's in the sterile surgical instruments in hospitals that have to survive harsh chemical autoclaves without degrading. It's the gleaming exterior of the Chrysler Building. It's lining the massive vats in food processing plants, ensuring acidic foods like tomatoes don't just eat right through the machinery.
Without chromium-enriched steel, humanity would be locked in a permanent, losing battle against thermodynamic decay. It is what allows us to build a world that actually lasts, resisting highly corrosive environments while maintaining immense structural integrity.
It is wild to think about the duality of it. The same atomic geometry that distorts light to make an emerald glow is creating this microscopic, self-healing armor on a subway car.
Yeah, it's pretty poetic.
And here is where the story of Element 24 takes a very dark turn.
Right. We have to talk about the chemistry of toxicity.
Because if you read environmental reports or if you've ever seen the movie Aaron Brockovich,
Classic example, yeah.
chromium has a notorious reputation as a severe hazard. But as we just established, we wear it in jewelry, it's in our kitchen sinks, it's completely safe in those contexts. So how does it suddenly become a dangerous villain?
This brings us back to the idea that an element's identity is defined by its context. The danger of chromium lies in the architecture of its outer electrons, specifically in what we call its oxidation states.
I think we need to break down oxidation states mechanically because this is where the Jekyll and Hyde transformation happens, right?
Exactly. So when an atom forms a chemical bond, it can give up, take, or share electrons. The number of electrons a chromium atom loses to form a compound defines its oxidation state.
Okay, simple enough.
And that loss dramatically alters the size, the electrical charge, and the overall behavior of the resulting molecule. Now, the two most common forms we encounter in the environment are trivalent chromium and hexavalent chromium.
Trivalent meaning chromium-3. It has lost 3 outer electrons.
Correct. And chromium-3 is the Dr. Jekyll of the story. It is a naturally occurring, highly stable form of the element. You find it in rocks, soil, plants, and animals.
So it's literally all around us.
It is. It's actually present in small amounts in our daily diet, and human biology is completely adapted to process it. In fact, many researchers consider trace amounts of chromium-3 to be important for human nutrition, particularly in how our bodies metabolize glucose and lipids.
So chromium-3 is stable, safe, and potentially even helpful.
Exactly.
But then we have Mr. Hyde, hexavalent chromium, or chromium-6. This is an atom that has been stripped of 6 outer electrons.
Right.
Why does losing 3 more electrons turn it into an environmental wrecking ball?
Because it changes everything about how the molecule interacts with water and with living cells.
That's-
Well, because chromium-6 has lost 6 negatively charged electrons, the remaining atom has a highly concentrated positive charge. To stabilize itself, it tightly binds with 4 oxygen atoms, creating a molecule called chromate.
And I'm guessing chromate doesn't just sit quietly in the soil like chromium-3 does.
Far from it. Chromate is highly soluble in water, meaning it can travel incredibly easily through groundwater and ecosystems. But the real devastation happens when it encounters a living cell. Chromate is a master of molecular mimicry.
Mimicry, you mean it disguises itself?
From the perspective of a biological cell, yes.
Oh, wow.
Because cells need certain nutrients to survive, right?
Oh.
One of which is sulfate. Now, sulfate is a central atom of sulfur surrounded by 4 oxygen atoms.
Oh, right.
Well, chromate is a central atom of chromium-6 surrounded by 4 oxygen atoms. Structurally and electrically, they look almost identical to the cell's transport protein.
Oh, that is terrifying. It's a Trojan horse.
Exactly, a Trojan horse.
The cell's own gates open up to pull in what it thinks is essential sulfate, and it accidentally drags in the chromate instead.
Yes. The transport proteins actively pump the toxin inside. And once the chromium-6 is inside the cell, the cellular environment is full of natural antioxidants. Things like vitamin C, for example.
Right, which we usually think of as good things.
Normally, yes. But these antioxidants immediately react with the chromium-6, forcing it to gain electrons and reduce back down into chromium-3.
Wait, but we just said chromium-3 is the safe, stable version. Shouldn't reducing it back to chromium-3 make it harmless?
You would think so. But outside the cell, chromium-3 is relatively harmless because it's too bulky to cross the cell membrane.
Ah, I see where this is going.
Right. Once it is generated inside the cell, that bulkiness becomes the fatal flaw. It is trapped. The chromium-3 forms highly stable, permanent bonds with the nearest available biomolecules, and very often that biomolecule is the cell's DNA.
It physically binds to the genetic code.
It binds to the DNA, it cross-links proteins, and the entire reduction process unleashes a storm of reactive oxygen species, these free radicals that just shred the cellular machinery.
That sounds catastrophic for the cell.
It is. This oxidative stress causes severe DNA strand breaks. And this is exactly why certain hexavalent chromium compounds are recognized as highly toxic and heavily carcinogenic, particularly when inhaled as dust or fumes into the vulnerable tissue of the lungs.
So the element itself isn't intrinsically evil. It is just governed by the strict laws of physics. If it's short 3 electrons, it's a stable nutrient. If it's short 6 electrons, it mimics our biology, breaks into our cells, and shreds their DNA.
That's the tragic irony of it. And the real tragedy of the Industrial Revolution is that for decades, heavy industry absolutely loved chromium-6. Because it is so reactive, it is incredibly efficient for industrial processes.
Let me guess. Anti-corrosion coatings, metal plating, and those brilliant pigments we were talking about earlier.
You got it. Leather tanning, aerospace primers, chrome plating for classic cars. Chromium-6 was the miracle chemical that made those processes cheap and effective, but the environmental cost was devastating.
Because it wasn't staying contained?
No, not at all. Workers inhaling the fumes suffered severe respiratory cancers, and improper disposal meant chromate leached into the groundwater, poisoning entire communities.
Which is why modern environmental science has had to completely reinvent how we handle element 24.
Yeah.
I mean, it isn't just about digging it out of the ground anymore. It's about rigorously managing its chemical state.
Yeah, we've had to develop entirely new fields of remediation. Today, industries use chemical reducing agents in their wastewater treatments to intentionally force dangerous chromium-6 waste to accept electrons.
So they convert it back into the bulky, stable chromium-3 form before it ever leaves the facility.
Exactly. It is a massive ongoing effort to clean up the legacy of the 20th century.
It's a sobering reality check, honestly. We extract these materials from the Earth, and we leverage their incredible atomic properties to build our modern world. But we can't just take the benefits and ignore the mechanisms. We have to take absolute responsibility for the chemistry we unleash.
It's so true. The story of chromium ultimately teaches us that the periodic table is not just a list of ingredients. It is a map of conditional possibilities.
Conditional possibilities, I like.
Yeah, because chemistry is rarely just good or bad. It is entirely about relationship and concentration. You take element 24, you tweak its electronic structure, and the very same atom that protects a skyscraper from collapsing, the same atom that colors a brilliant emerald, becomes a deadly hazard.
It really makes you look at a simple stainless steel fork sitting on your kitchen counter with a completely different level of respect.
I know.
There's a whole invisible high-stakes drama happening right there on the surface, brokered by this one incredibly versatile element.
And that drama is playing out in the engine of your car, in the screen of your smartphone, and in the bedrock of the Earth every single day.
But before we wrap up, considering everything we've uncovered about how sensitive chromium is to its environment, how just a shift of a few electrons changes it from a protector to a poison, it makes me wonder about the rest of our infrastructure.
What do you mean?
Well, we tend to assume the materials we use every day are fixed. But how many other dormant Jekyll and Hyde elements are sitting inside our modern technology just waiting for the right environmental trigger or the wrong chemical reaction to suddenly flip into a completely different, potentially dangerous beast?
Oh, wow.
I mean, we think we've mastered these elements, but we might just be keeping them temporarily balanced.
That is a very unsettling but highly relevant question for modern materials science. The periodic table is full of sleeping giants, and we are heavily reliant on atoms we only partially understand.
Something to think about the next time you look at the metallic shine of your appliances. If you enjoyed this journey through Element 24, follow Atomic 118, like this episode, and share it with someone who loves science. And remember, the periodic table still has 118 stories, and the next one may be even more surprising.
It certainly will be, because while chromium has mastered the art of brilliant color, invisible protection, and molecular mimicry, the very next element sitting right next door on the table is waiting to show us how a metal can actually breathe life into the bottom of the ocean and act as a microscopic battery for the human brain. But we'll leave that mystery for next time. Keep questioning the world around you, and we'll see you on the next deep dive.